So my name is Laura Mayorga. I'm at the Johns Hopkins Applied Physics Lab, and it is my distinct pleasure to introduce our first speaker, Zifan Lin, who will speak to us about a search for thermal excess in rocky exoplanets. Take it away when you're ready.
Test. Can you hear me okay? Hi, good morning, everyone. I'm Zifan. I'm a postdoc fellow from Washington University in St. Louis, working with Professor Tansel Dalen. And today, first of all, thank you all for coming here early. Hopefully, I can wake you up with some exciting exoplanet science. So I'll be talking about a search for thermal emission excess in rocky exoplanets. And just to make sure we're on the same page, when talking about thermal emission excess, right, I'm talking about the day-side infrared emission of planets. So usually observed during the secondary eclipse. So before and after the eclipse, we have both the emission from the planet's day-side and also the star. And during the eclipse, we only get the star stellar signal. So we subtract both, and we get the emission spectra of the planet's day-side. So that's simple. That's great. And for most rocky planets, they are on short orbit and they have like high temperature. They're usually tidally locked because they are just so close to the star. And usually they have like a permanent day side, permanent night side. And at the stellar point, that would be the hottest point because this is like directly heated by the star. And the temperature at the substellar point are defined as irradiation temperature, or TIRR, is defined as such, and it is assuming zero albedo, so no light gets reflected, and zero heat redistribution, so no heat gets transported away. So that is actually the theoretically maximum temperature you can get at the planet's surface without any additional heat source other than the star. And of course, we are looking at exoplanets that are light years away, and we don't have any spatial resolution. So we are only measuring the integrated day-side temperature of the planet. We are only seeing it as like one data point. We don't have any spatial resolution. So we are measuring the day-side emission temperature or brightness temperature, T-day. And there's this one ratio defined as R, or T-day over TIRR. And theoretically, it should be smaller than or equal to 1 because like TIRR is the maximum temperature allowed. And of course, as you can see, there's a question mark there. So the thing is not that simple. So here, what I'm showing is the irradiation temperature of planets on the horizontal axis, and also this R fraction on the vertical axis. And all these arrow bars are measurements for exoplanets. And as you can see, there are some planets that are behaving pretty well. So if the pointer works, yeah. So these planets, they have R equals 1, which means they have zero albedo, they don't have heat redistribution. So they are just dark bare rocks, right? They don't have atmosphere to transport heat away. And there are some planets that with R that's like around 0.9, and that's also good because that means they just have a reflective surface, but then they don't have atmosphere, which is expected for these like hot planets with like thousands of like 1,000 or higher equilibrium temperature. And of course, there are also some planets that have a little bit lower R, which can be indicative of a rock vapor atmosphere, right? That gets the heat transported to the night side. So that decreases the day side temperature a little bit. But if you see the top of this figure, you can see that some planets are actually problematic because they have R greater than 1. And that is theoretically not possible. So what is going on here? And just a little bit of solar system in context, right? For some of these very hot rocky planets, we are expecting them to have like alkaline metals like sodium, potassium evaporating from their mantle. And that is actually what we see for our own Mercury. So that's just a little bit of context here. And if you zoom in, right, to this part of the figure, so these planets are all rocky planets orbiting M dwarfs, or so-called M Earths. And you can see there's actually some kind of like positive trend here coming from like this Coy et al. 2025 paper, right? They identified this kind of positive trend, and I want to figure out if this trend is real, and if it's real, right, what is causing this positive trend, and what is causing this very puzzling thermal excess? So what I'm trying to do here is I'm trying to do a systematic simulation and also like filter of targets among all exoplanets. So I will start with all exoplanets, and then I can use my interior model and also some tidal induction heating and residual heat model, right, to figure out what is their thermal excess potential, or what is the maximum delta R that is allowed for each of these planets that can possibly bring their thermal emission above 1. And I can identify the best targets for future surge of thermal emission by, for example, JWST or even future Roman. So just as the first mechanism that can possibly produce a thermal excess is tidal heating. So as we know, like when a planet has non-zero eccentricity, right, when it's orbiting a star, it's going to suffer some kind of tidal heating that's like warming up its interior. And this is exactly what I'm trying to model here. So I'm just using this very simple so-called fixed Q approach, which is the tidal heating rate F tidal equals a combination of all things, including eccentricity, including its distance from the star, and most importantly, this tidal property, or the imaginary part of the K2 love number. So for Earth, this number is like around 0.003. And for Io and for like some other extremely tidal heated planets, this number can be higher. And what I'm showing here, again, is the irradiation temperature of planets versus their tidal heating rate, F tidal. And all these planets colored in red or blue, they are color-coded by their eccentricity. And these highlighted planets are rocky exoplanets. And all those gray planets in the background are like all other planets. And just as a note here, I define rocky exoplanets or the probability of being rocky, P rocky here, using this kind of interior model. Like I try to like sample thousands, tens of thousands of data points allowed by their mass and radius error bars and see if they are under the pure rocky compositional curve. So yeah, just a note on the definition. And using this kind of simple model, I calculated their delta R due to tidal heating, which is simply the ratio between the tidal heating plus the insolation heating over insolation heating. So that's the energy coming from the star. And this is like the factor that tidal heating can cause the thermal excess. And as you can see here, right, what I'm showing in log scale here, the delta R is actually pretty small. For most of these rocky planets, they are smaller than 10 to the minus 2. So assuming an Earth-like tidal property. So if you plot their 1 plus the delta R versus their irradiation temperature, all those planets are going to concentrate near this like R equals 1 line. They are not going to have a positive trend unless you increase the tidal property to a very, very high value, which is like similar to a extremely theoretically predicted tidal heated planet, exoplanet. So like these planets, they are not going to explain that positive trend. And there's another possibility, which is in induction heating. So when a conductor is moving through a changing magnetic field, it's going to feel electrical current, and that electrical current can hit its interior. But again, I'm showing like this plot from this paper, and they're predicting that a induction heated planet can have like an Io-like or Earth-like tidal heating rate. But as I just showed, that tidal heating rate is actually not that much. So induction heating maybe is not the best explanation for the thermal excess as well. And here I'm showing this like kind of evolutionary diagram from one of my recently published work. This paper actually is not directly related to this project, but it is actually investigating what is the possible origin of this kind of so-called high-density exoplanets. So one of the explanations is that these high-density exoplanets, they used to be under the pressure of like a enormous, like massive gaseous envelope, right? And that envelope is supplying pressure to the interior and compressing its interior to a higher density. But what I learned from this project is that like the thermal evolution of this kind of planet is actually quite complicated. So you have a global mag motion just because you have such a thick atmosphere that can very efficiently keep the heat inside. So that mag motion is going to right, first of all, the planet is going to experience atmospheric escape, and then that mag motion is going to cool down. So what I'm trying to investigate here is like how long this entire process takes, right? So you can have this tau or like time scale for atmosphere loss plus mag motion cooling down. And when the planet is in this stage, right, it can have actually thermal emission excess just from the cooling down mag motion. And that is why like I try to compare the stellar age versus like ES emission spectroscopy here, just identify some young planets that are possibly still in this cooling down process. But this part of the project is still under development, so there will be detailed escape and also cooling model in the future. And of course, like given all this discussion, I'm ignoring two very important mechanisms or two elephants in the room here. So they are both related to the surface property of the planet. So of course you can have a albedo difference, right, given the different compositions, and that can actually explain part of that positive trend. It can explain R smaller than 1, but of course you cannot have a negative albedo, so you cannot explain R greater than 1 with surface properties. And there's also this like so-called thermal beaming mechanism, which comes from the fact that when you're seeing planet, you're only seeing the illuminated side, you're not seeing the parts in shadow. So you can actually overestimate R, and this can actually explain R greater than 1. So these are also things to consider. And I will put my summary here. So in this project, I'm trying to systematically investigate all these possible mechanisms that can cause a thermal excess in rocky exoplanet. And these good targets for the search of thermal excess can allow us to understand better planet formation evolution and also their surface processes. And they can be very helpful for future missions like the JWST Rocket War CDT or Roman. And thank you very much for your attention.
Questions for our speaker?
Thank you. Very interesting topic. Have you considered the possibility of non-tidal locking? Even slightly non-synchronous rotation could give you a lot of extra heating.
Can you maybe elaborate the question a little bit, what is causing the heating in this case? Is it still tidal heating, but they're coming from some kind of or orbital maybe instability just due to not perfect tidal locking? I guess in this case, I'm only considering yeah, in this very simple mechanism, it's just the orbital parameters and eccentricity. So I'm not entirely sure what you're referring to. If you can point me to some papers, that we greatly appreciate it. Yep.
Other questions?
I had something on my mind. And in our solar system, we got a lot of heating because of impacts. We think we got the moon. There was, of course, the late heavy bombardment. Is there any chance that either that causes the remnant, or is this a process that will be occurring now?
Yeah, I guess that's somehow combined with the last mechanism that I mentioned here, right? Of course, you can have primordial heat maintained by the atmosphere and then magma motion cooling down. And of course, you can have an impact and then generate magma motion and that cools down. So that's the last stage here. So that's somehow combined. And I can, for example, include some impact probability model, what's the frequency, how often they all happen, and try to add that into the equation. Yeah.
All right, let's thank our speaker.